So one last example problem for the day. I would like you guys to to draw the Lewis structure for chloroform, CCl4. Once you have this structure drawn, right, for some good practice, just drawing more Lewis structures, before also looking at the electronegativity table, I would like you to predict whether the bonds in this compound are going to be nonpolar bonds or if they're going to be polar bonds, just based off of the location of carbon and chlorine on the periodic table. Are they close enough that you think that they would be similar enough that you have a nonpolar bond, or are they far enough away where you think that the electronegativity values are going to be different enough to give you a polar bond? Once you have your prediction, then please go back to the electronegativity table and kind of confirm what your expectations were, right? So we're going to hypothesize an outcome, and then we're actually going to go double check what the outcome is. Welcome back from the pause. Let us go through. We're going to draw this structure. We're going to predict the bonding, polarity, and then we're going to actually calculate what the electronegativity difference is between carbon and chlorine. All right, so first and foremost, we have to figure out what the valence electron count is in this molecule. That way we know how many electrons we're actually working with that we can take and then place back inside of the molecule. Well, our carbon has a total of 4 valence electrons, and there are 4 chlorines, each with 7 valence electrons. I just almost started writing chlorine there. The total then of 4 plus 4 times 7 gives us a total of 32 valence electrons. All right, so in actually starting to draw the molecule then, we're going to pick out the element that has the greatest bonding capacity. This will again be our carbon, and we're going to surround this carbon with 4 chlorines. Chlorine, 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 and chlorine. This means that we have placed a total of 2, 4, 6, 8 electrons around the atom, or around the molecule so far, giving us a total of 24 valence electrons left. The 24 valence electrons we're going to add to the terminal chlorines first. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. All 24 electrons have been added, giving us none left over. So let's double check that everything's satisfied. Our chlorine has 2, 4, 6, 8 electrons around it, and that will be true for the rest of the chlorines. They all look the exact same. And our carbon in the middle also has 2, 4, 6, 8 electrons around it, so everything is perfectly satisfied. This is a stable molecule. No reason to be pushing electrons around to make double bonds, triple bonds, whatever. There's no need for it. Similarly, there are no charges here that we need to add or subtract, so this is perfectly satisfied and our structure is finished. All right, next up, we are going to try and predict whether or not the compound is going to be, or the bonds in the compound are going to be nonpolar or polar. Well, on the periodic table, both carbon and chlorine are present in the P block. So they're both on the right-hand side of the periodic table. Carbon is up here, and our chlorine is down here. The question is this difference enough to make the individual bonds polar? Well, first and foremost, let's predict which of these two is going to have a higher effective nuclear charge. As we saw back in chapter 4, the effective nuclear charge really increases as we move from left to right on the periodic table, meaning that chlorine is going to have the higher effective nuclear charge. If the bonds end up being polar, we would expect chlorine to have the higher electronegativity and pull the bond away from carbon towards it. Again, the kind of remaining question is this distance, though, on the periodic table actually enough to make a polar bond? And you know what? Let's just say, for all intents and purposes, we're going to predict yes. Let's say that there is going to be a polar bond here. And also, as predicted, our effective nuclear charge increasing from left to right means that the chlorine is going to be the more electronegative. So let's represent this by saying each of these bonds are being pulled away from the carbon, so there's a little bit of a positive residual charge on the carbon, and the electrons are being pulled towards the chlorine. We're going to do that for each of these bonds here. That is going to represent in our Lewis structure a difference or a polarity in our bond in one direction away from carbon and towards chlorine. All right, well, let's go back to our actual table to confirm this hypothesis, or maybe even refute the hypothesis. When we go back to our electronegativity table, and again, I'm going to clean this up a little bit, we need to pick out our chlorine and our carbon. Well, we can see based off of our prediction that we made using our effective nuclear charge difference, chlorine actually does have a higher electronegativity. The question is this difference enough to make an actual polar bond? Well, chlorine's electronegativity difference is 3.16, or electronegativity value, sorry, is 3.16, and we're going to calculate a difference from carbon's electronegativity value. The difference between 3.16 and 2.55 is equal to 0.61. Now, on the ultimate scale of bond polarity, the value of 0.61 is not incredibly polar, but it is still greater than 0.5, and it's greater enough to say, yeah, this is a polar bond. The electron pair between carbon and chlorine is better stabilized by chlorine. And so the Lewis structure, going back forward again, that we have drawn here, where each of the bonds are being pulled away from carbon and more towards the chlorine, is a perfectly accurate way to try and represent or draw where the electron pairs are inside of this structure. Chlorine's going to be holding the electron pair most of the time as it oscillates between it and the carbon. Overall, the structure, though, is very stable. Cl4 is a readily abundant molecule that we can synthesize and make and store, in our world. So even though the bonds are polar, this doesn't mean necessarily that the structure is unstable. It just means that the chlorines are better at stabilizing the bonds themselves.